Good day, I'm Norman Wobbeler. So we've been introducing a new way of thinking about matrix algebra via these things called maxils, which are multi-sets of pixels. And it turns out that the usual matrix multiplication is really a consequence of this more fundamental pixel multiplication, which is just happening at the level of pixels. So a pixel is a little two-list consisting of natural numbers, and here's how we multiply two such pixels. KL times MN is going to be the pixel KN if these intermediate ones are equal, if L equals M. And otherwise, we get emptiness, nothing at all. We like to visualize our pixels as forming a part of a screen that extends to the right and down, with the standard kind of labeling 1, 1, 1, 2, 1, 3, and so on, 2, 1, 2, 2, 2, 3, and so on. And there's also these diagonal elements where the two coordinates are equal that plays a particularly interesting and important role. Okay, we want to understand the geometry of this multiplication. And that's going to really help us understand matrix algebra, which of course is a key topic in mathematics. So today we're going to have a rather precise look at how this multiplication figures in the context of the geometry of this screen. So let's have a good look at a particular pixel and some of the geometrical aspects that it determines on our screen. So let's consider a pixel A consisting of the natural numbers K and L. On our screen, we can picture that A as a position on our screen where the row number is K and the column number is L. Now this pixel determines some other things. In particular, it determines a row. This row that's labeled or indexed by K we'll call the row of A. And correspondingly, this column indexed by L will be called the column of A. This row and this column of A determine two additional points because they meet the diagonal in two additional points, which might coincide with A if A happens to be on the diagonal, for example. We're going to call this point here the row pivot of A. So it's the place where the row of A meets the diagonal. It's the pivot consisting of the pair KK, KK. And correspondingly, this point here, place where the column of A meets the diagonal, will be called the column pivot of A. Its coordinates are LL. So we have the original pivot, we have the row of A, we have the column of A, we have the row pivot of A, we have the column pivot of A. We also have two secondary rows and columns. This row here, the row through the column pivot of A, will be called the transpose row of A. And this column here through the row pivot of A will be called the transpose column of A. So altogether, A determines its row and column, together with a transpose row and column, which pass through the pixel LK, which is the transpose of A. So that's a nice sort of fourfold aspect. There's a little square here determined by this this pixel A. So these are interesting and useful geometrical things associated to the pixel A that will be involved in the multiplication operation. So now let's look at what happens if we take our pixel A and multiply it on the right by some other pixel X. What are the possibilities for getting another pixel? So here is A, it's the pixel KL, and we want another pixel as a product. So let's suppose that we're multiplying by LN. We have to have these two things equal if we're going to get something that's non-empty. So let's assume that we're multiplying by a pixel X of the form LN, in which case the product is KN. And we want to understand the geometry of that story, and there's sort of two cases that we can consider. So the first case here, we have A sitting somewhere here above the diagonal. Here's the row and column of A. Now have a look at this X pixel. It's LN. What does that mean? Well, it means that its first entry is L. That's saying that it's actually in this row somewhere, the row indexed by L, which is just the transpose row of A. So if we take the column of A, which is indexed by L, and go down to the diagonal, then this row will also be indexed by L, because everything on the diagonal is of the form LL or MM. Okay? So that's how we get this transpose row. We go down or up the column of A till we hit the diagonal, and then we go across. And this formula is telling us that in order to get something that's non-empty, of the form A times X, we have to have X being on this transpose row. So X must be in the transpose row of A. And if it is, let's say here, then where is this product, A times X? Well, the product is Kn. Where is that? Well, that's also in the row of A, because A has first entry K, and this product has first entry K. So this product, A times X, is also in the row of A. And where in that row is it? Well, it's the same column as our point X. So X has second entry N, and so AX also has second entry N. That's telling us that if we know where X is, then AX is in the column of X. And notice that X could be anywhere along this transpose row, and wherever X is on that transpose row, the AX product is correspondingly in the same column, but just in the row of A. So if X were here, then AX would be here. If X is here, AX would be here. So as X moves along all possible positions in this row, and it could be very far out, the product AX is defined and is correspondingly on the same row as A, but just in the same column as X. Now the story is exactly the same when A is below the diagonal, so nothing really changes except that the picture looks a little bit different. All right. So here is A, here's the row of A, and here's the transpose row of A. So in order for A times X to be a valid pixel, we want X to be on this transpose row of A. So in this case, A being here, X can be anywhere on this transpose row. And wherever it is, we go in the same column to get A times X. So this is just another way of thinking about the algebra. This is the algebra, this is the geometry. It's telling us that if we want to multiply A times X, then the final thing is going to be in the same row as A, and it's going to be in the same column as X. Right? And that will only happen when A and X are related by having the common L here, and that's really the condition that the column of A and the row of X meet at the same diagonal point. Now when you're doing a lot of matrix multiplications in linear algebra or in group theory or in many other related areas of mathematics, ultimately these kinds of geometrical insights are often quite useful. But they're maybe not spelt out so explicitly in traditional linear algebra courses because there's the emphasis on matrices rather than on the pixels themselves. So we have a different orientation here which allows us to see a somewhat different aspect of things, but it's really the same kind of underlying algebra, just we're reviewing it slightly differently. So very useful to absorb this relatively simple geometry associated with this kind of product. How to form a product A times X, where A is fixed and X is a variable. Of course, now by symmetry, we have to look at the other case. What happens when we take our fixed pixel A and multiply it on the left by a pixel, say Y? So what happens when we look at Y times A? So here's A now on the right, and here's a Y on the left. And in order for this product to give us something, these two inside ones have to agree. So this has to be a K. This can be anything it wants to. Let's call it J. So if we have JK times KL, then the result is JL. And we see that this Y, JK, must be in the transpose column of A. That's the condition, essentially, that this second entry of Y agrees with the first entry of A. So let's have a look at the geometry, in this case here where A is up here. Here's the row of A. Here's the column of A. Here is the transpose row of A that we've already looked at in our last slide. Here's the transpose column of A. So this column here consists of things which have their second entry the same as the first entry of A. This is the row of A. It's everything that has first entry K. This is the transpose column of A. It's everything that has second entry K. So what we're saying here is that the Y that we're choosing to multiply with A, Y on the left, A on the right, has to be from this transpose column of A. And it can be anywhere in there. The other index J is just the index here that determines what row this Y is in. So as we move Y up and down this column, then the product YA will move up and down this column. Because this YA has the same row as Y. You see the J and the J here agree. That's saying that these two are in the same row. While this YA and A have the same second entry. It means that they're in the same column. So this is in the same column as A and the same row as Y. So as Y moves up and down this transpose column of A, then correspondingly Y times A moves up and down the column of A. So in such a way that the row of Y and YA are always the same. So the product YA can be any pixel in the column of A. The end result has to be a pixel in the column of A, just as when we multiplied A times X, the net result was a pixel in the row of A. So whenever we multiply A by anything, we're getting either a pixel in the row of A or a pixel in the column of A. The other sort of picture that you might have is an A below the diagonal. The story is the same there. Here's the column of A. That's where YA is going to end up. And here's the transpose column of A, obtained by going along the row of A until you get to the diagonal and then choosing the column there. So Y is allowed to be any place on this transpose column. In fact, it could be down as much as it likes to be. And correspondingly, YA is going to be on the column of A, but at the same row as Y. So if Y was up here, YA would be here. If Y was here, YA would be here. So it's just a flip of the previous situation. Relatively simple, but still one has to stare at it for 10-15 minutes and become familiar with it, have a look at some examples, say what happens if A is here, and what can we multiply A by to get what? So it's good to just play around with some diagrams so that you become familiar with what happens when you multiply A by either an X pixel on the right or a Y pixel on the left. So to summarize, if we have a pixel A, then if we multiply it by X on the right, we're going to end up with a pixel somewhere on the row of A. And if we multiply it by a pixel Y, then we'll end up with something that's on the column of A. So the possible products that we can get by multiplying a pixel by A lies on this cross, consisting of the row and the column of A. So let's give that a name. Let's call that the cross of A. That consists of both the row and column of A. And these are the pixels of the forms AX or YA. Here are the AXs. Here are the YAs. And now, of course, when we're doing linear algebra, we want to go to the maxils. Maxils are multi-sets of pixels. We're considering not just one pixel, but a whole bunch of pixels with multiplicities. And we're going to agree that to represent a maxil in this picture, we're going to record the multiplicities that various pixels occur, and just write down those multiplicities in the corresponding spots of the pixels. So this pixel here, maybe it's the pixel 1, 5, say, then this 1 here means that there's one of those. This 3 here means that whatever pixel this is, maybe it's 4, 7, then that means that there's 3 such pixels 4, 7 in the maxil M. And there's 5 of these pixels, and there's 5 of these pixels. So suppose that's the maxil. It consists of 1 of these, 3 of those, 5 of those, 5 of those. So such a maxil M also has rows and columns, namely the rows and columns of its pixels. So associated to this maxil, we could also consider various rows, namely this row, this row, this row, and I see that I've forgotten that row. So let me add that. That's also a pixel in our maxil, so it also gets a row, and I see I've forgotten this column. Okay. There we go. Okay, so now we have 4 rows associated to this maxil, namely the rows of the pixels that it contains, and 4 columns also associated to this maxil. And together, we'll say that this is the cross of M, sort of in correspondence with this thing here. So the cross of M consists of all these rows and columns through the various pixels of M. Now a moment's thought shows that these are going to be the possible pixels contained in Mn or Om. If we multiply M by any other pixel, then we just have to multiply that other pixel by each of the pixels in the maxil M, one at a time, and count the multiplicities of all the pixels that are generated. And if we multiply on the right, something like Mn, then we know that at the individual pixel level, the pixels that we're getting are all in these rows, the rows of the pixels of M. And if we multiply on the left, say Om, then for each of the pixels that we're multiplying, we're going to get pixels which lie in the columns. Now if we multiply by a maxil rather than a single pixel, either on the right or the left, well, the story is just a multi-set version of that. Instead of getting one pixel on one of these rows, we're getting a whole bunch of pixels, but still on these rows, or still on the columns if we're multiplying on this side. So you take this maxil M and you multiply it by any other maxil, doesn't matter how big or complicated it is, the result has to be another maxil whose support is contained in this cross, consisting of these rows and these columns. Of course, if we know about the cross of n, then the thing is symmetrical, so the products of the pixels here have to be in the cross of M, and they also have to be in the cross of N. So that gives a rather stringent constraint on the pixels that can arise when we multiply two maxils. And so I think you can see the usefulness of this geometrical point of view, that we can sometimes almost visualize what's happening with this kind of multiplication of pixels or maxils. Now there's a third way of looking at this multiplication. So if A times B equals C, and A, B, and C are pixels, we've sort of looked at things from the A point of view, and we've looked at things from the B point of view, but we still can look at things from the C point of view, and that gives us another important insight into what's going on. So let's do that now. So we could ask the question, given a pixel C, what pairs of pixels A and B will multiply to get A, B equals C? So suppose here is our pixel C, and we're interested in how can we find pixels A and B somewhere on the screen so that A times B is going to give us C? Well, we already have enough information to answer this, because first of all, A must be in the same row as C. Because we know that when we take the pixel A and we multiply on the right by something, then what we get is in the same row as A. So if C is in the same row as A, well then A must be in the same row as C. And that means that the A in this equation has to be from the row of C. Similarly, B must be in the same column as C. Why? Well, because we know that when we take a pixel B and we multiply on the left by some other pixel, that what we're getting is in the same column as B. So that means that C must be in the same column as B. But that means that B must be in the same column as C. So the B that works in this equation has to be in the column of C. So if we want to find an A and a B that multiply to C, we know that we have to choose A in this row and B in this column. Anything else is a waste of time. You're not going to get a product that multiplies to the pixel C. Okay, but there's one more thing that's required. So, for example, suppose that we choose an A in the row of C, and now ask, okay, how are we going to find the B that multiplies together with this A to give us C? Well, remember that from the A point of view, if we want something to multiply the A, we need to look at something which is in the transpose row of A. This B must be in the transpose row of A. So if here's A, we go up its column to the diagonal, to the pivot, column pivot of it, then the row through there is where B must come from. We can only multiply A by something in this row. So this B that we're looking for must be in this row. But we've also just said that it also must be in this column. So there's only one place where it can be, namely right there, in the meat of this row and this column. So I've said that here. So for each pixel A in the row of C, we pick an A in this row, the corresponding B must be the meat of the column of C and the transpose row of A. So if A moved from here over slightly to the left, for example, the corresponding B would still have to be in the column of C, but it would now be in the transpose row of this thing, which would be there. So as A moves in this direction, the corresponding B would have to move in this direction. And as A moves in this direction, the corresponding B would have to move in this direction. If A was far out here, B would have to be far down here. Or we could interchange the story and say that If we know B, then A must be the meat of the row of C and the transpose column of B. That's just the symmetrical version of it. So let me illustrate that reasoning in an explicit kind of example here. So here's our screen, and now I've separated it into little pixels, so they really do look like pixels. There's the pixel 1, 1, pixel 1, 2, pixel 1, 3, and so on. And we've chosen a particular pixel C right there. So let's ask the question, what are the various products of pixels that will multiply to get C? We're looking for an A and a B that multiply to get C. So what we've just determined is that A has to be in this row and B has to be in this column. So suppose we choose the first A in this row, call it A1. There it is. It's actually the pixel 3, 1, but we don't really care about what it is exactly. So corresponding to this A1, what is the B pixel that we have to choose in order that the product of this A1 with the corresponding B gives us exactly C? Well, we have to go up here to the diagonal and then across until we meet the column of C. That's exactly that one there. So the first pixel in this row has to multiply with the first pixel in this column to get C. So A1 times B1 equals C. And now the second pixel, A2. So we go up the column of A to get its transpose row, and then across there to get B2. So this A2 is going to multiply with this B2 to give us C. And then this A3 is going to multiply by B3. Okay, B3 is the third one here, which happens to be C. Okay, let's call it B3 for consistency. So A3 times B3 will also give C. Then A4 times B4 will also give C. A5, which is also C, times B5 will give C. A6 times B6 will give C. A7 times B7 will give C. And so on. We can keep going along here and multiplying the corresponding A with the corresponding B, and each stage we're going to get C. So this is the Maxwell equivalent of the row vector times column vector multiplication that is so familiar in linear algebra. The idea that in order to do matrix multiplication we have to multiply rows with columns, and the way we multiply them is to take this times this, plus this times this, plus this times this, plus this times this, and so on. So at the level of Maxwell's, instead of pixels, we would have multiplicities here. Maybe there would be a 2 here and a 5 here, representing 2 of these and 5 of these. And maybe there was a 3 here and a 7 there. So when we're multiplying this pixel times this pixel, we really have to multiply 2 of these ones with 3 of those. So there'll be 2 of these times 3 of those will give altogether 6 of those. That's why we have to multiply 2 times 3. And then if that's 5 and 7, whatever I said, so 5 times 7, that'll be the number of pairs, pixels here times pixels there, that give us C again. That's why we have to go this times this, plus this times this, plus this times this, plus this times this, plus this times this, etc., to get the coefficient of that pixel in the product. So this is just a restatement of very familiar multiplication in matrix algebra, but it's a different story really, because we're operating now in a free kind of domain where there's no more bounds on the extent of this Maxwell or these Maxwells. We're not restricting ourselves to matrices of a particular kind here. These are general rules that apply whenever we multiply 2 Maxwells. Okay, so I hope you've absorbed that. We're now ready to practice some Maxwell multiplication. All right, so let's have a look at some Maxwell multiplication. I'd like to start with something relatively simple and something with some pattern to it so that it's possible to sort of see or look for some generalizations. So I'm going to consider very simple kinds of Maxwells that just are uniform over some little rectangle, in fact some corner rectangle. So let's consider this Maxwell here times this Maxwell here. This is a picture of the Maxell. The actual multi-set would be the pixels 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and 2, 3. And here the Maxell would be the multi-set consisting of the pixels 1, 1, 1, 2, 2, 1, and 2, 2. So we have 6 pixels here in this multi-set. We have 4 pixels here. The way we multiply these Maxells is we have to multiply each of these 6 pixels by each of those 4 pixels. So there's 24 possible products. Many of them, in fact most of them, will give us emptiness. Only some of them will actually give us legitimate pixels which end up configuring in the product. So let's adopt that position that we were looking at just in the previous slide and ask ourselves, let's say this thing here, how can we figure out what the multiplicity of the pixel 1, 1 is in the product? So if C is 1, 1. So the only way of getting this thing as a product is to take something from its row in the first Maxell times something in its column in the second Maxell. And we saw that the only way of getting this thing here is actually to take the first thing in this first row times the first thing in this first column, or the second thing here times the second one, or the third here times the third one, and so on. So there's a product 1 times 1 that will give us one of these, and there's also the product of this one times this one, which will give us one of these, and there's no other possible products that will give us the pixel 1, 1. So there's altogether 2 ways of getting the pixel 1, 1 as a product. That just corresponds to the multiplication of this row times this vector in the usual linear algebra story. Similarly over here, this too results taking this row, this first row, times this second column, because this is the 1, 2 entry, so its row is this one and its column is this one. And so this times this, plus this times this, plus then there's only zeros. This one is this times this, plus this times this, and zeros. This one is this times this, plus this one times this, and zeros. And there can't be anything else because the product of this Maxell with anything else has to be supported in the rows of this Maxell. Remember that when we take a pixel and we multiply it by something on the right, we're getting something in the same row. So if you take all of these pixels and multiply it by anything at all on the right, we're getting something that accumulates in the same rows as those things. So the product has to be in the first 2 rows. And similarly, when we multiply this Maxell by anything on the left, what we get has to have elements only in the same columns as we have here. So in other words, only the first 2 columns can arise. So if we combine those 2 facts, we know that we multiply this times this. We know that what we're getting has to have the property that all the pixels are contained in the first 2 rows and they're contained in the first 2 columns. So that means that they're in fact contained in this little 2 by 2 square. So similarly for this one here, here's a similar kind of bigger Maxell with a uniform support over this little rectangle. It's a corner rectangle, 5 by 3. Times this one, which is a 2 by 4. And so we have various possible products. So for example, this thing here, this 2, where does it come from? Well, we would take the second row, because that's in the second row, and we would take the 4th column over here. So we have to multiply the second row here with the 4th column there. We go 1 times 1 plus 1 times 1, and then there's no more non-zero things, so a total of 2. Okay, and here's something to tell us that this kind of thinking doesn't necessarily restrict to just rectangles which are corner rectangles. So here's somewhat of a more general rectangle. It's kind of floating a little bit more in the middle. This one here has a row of zeros above it. If we multiply this Maxell with this Maxell, then you can check that what you're going to get is this Maxell over here. It's the same kind of story. So say to get the coefficient there, we would look at the row that corresponds to that pixel in the left-hand maxil, and the column that corresponds to it in the second maxil. So we have to multiply this third row here with this second column here. So that's 0 times 0 plus 1 times 1 plus 1 times 0, etc., to give us 1. So all these empty blanks are, of course, zeros. We could put zeros in here, but it's not going to add any information. Okay, so it's already a little bit interesting. So there's now an exercise to play around yourselves with doing some maxil multiplication, perhaps with just relatively simple maxils that are supported on rectangles. But maybe the rectangles don't have to be corner rectangles. They can be sort of floating anywhere. You can experiment with different possibilities and see if you can figure out a kind of rule or figure out the pattern so that you could predict what the product of any two rectangles is without actually having to go through the thing step by step. But it's certainly useful to work it out step by step, really examine what's going on at the pixel level. This is a really fundamental multiplication in mathematics. Okay? So beyond the arithmetic of numbers, we have the arithmetic of polynumbers or polynomials. And then the next step is the arithmetic of matrices, which is now taken over by the arithmetic of maxils. So this is a very, very fundamental and huge step to extend our notion of arithmetic from one-dimensional arrays to two-dimensional arrays. We're now multiplying two-dimensional arrays, or maxils, here. And it's very important, and it's such a vital ingredient in many topics in mathematics. So I hope you enjoy the freedom here that you have, that you don't have to worry about the size of the underlying matrices. The matrices themselves are only playing a secondary role. They're only a way of picturing maxils. It's really the maxils themselves which are the main object. And here's a bunch of examples of another kind of maxil multiplication involving objects which are sort of triangular in shape. So these are maxils that are also relatively simple. They all have uniform multiplicities. That's relatively simple. But we're considering things that have a sort of triangular aspect. So two of the sides are vertical and horizontal, and the other one is sort of sloping down at a slope of 1, parallel to our diagonal. And here, 1, 1, 1, 0, that's an upper triangular kind of thing. Here's a sort of a lower triangular maxil. And you can check that the result is 2, 1, 1, 1. And here with this lower triangular one and this upper triangular one, so exactly the same 2 is involved there, but now in the opposite order, we get something that looks a little bit different. 1, 1, 1, 2, 1, 2. Here we have a little bit of a bigger one. There's an upper triangular one, which is sort of corner justified. And here's a lower triangular one, also corner justified. And we see that we get this particular somewhat pleasant little pattern for the product of the maxils. Here is another example, a bigger lower triangular. And here's an upper triangular one that's shifted a little bit, so it's no longer justified. It's no longer a corner object. It's sort of floating a little bit, but still its diagonal is on the main diagonal of the screen. And the product, you can verify, see if I've done it correctly, is this pleasant little square here with a fringe of 1s and then a fringe of 2s, a fringe of 3s, and a fringe of 4. Kind of the opposite of the kind of thing that we saw in this one here. So already, just in this sort of simple kind of very specialized subcase, we're only multiplying upper triangular or lower triangular maxils, uniform. We can see that there's some kind of combinatorial thing going on. There's a pattern to discover and play around with, and so you can get a little bit of experience with pixel and maxil multiplication by trying to figure out if you can find some pattern that allows you to predict what happens if you multiply two triangular maxils. And you might try what happens if we multiply an upper triangular by another upper triangular one, for example. What are the possibilities? What happens? Can you predict what happens? Alright, in our next video, we of course want to say a little bit more about this Maxwell algebra and connect again a little bit more with traditional matrix algebra. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.